Thank you for joining us for this brief presentation on 2.5 axis milling in SolidCAM, the certified gold partner fully integrated CAM solution for SolidWorks. As you'll notice, SolidCAM is found directly inside the SolidWorks user interface. We'll start a new milling project. We'll assign the coordinate system by simply selecting on the face that we want parallel with the XY axis. If we need to move the origin, you can simply pick a new location. There are also a number of methods for realigning the axes as necessary. Next, we will define the stock. We'll use 3D model in this example, and we'll define this from the available machine configurations using the casting stock. Next, we'll assign the work material, and we're ready to begin machining. The first operation will be a face mill. We'll select the geometry, choosing from the model, to define the body that we want to cut. Next, we'll choose a tool by selecting from an import library. We'll choose this 4-inch face mill. Setting the levels is as easy as choosing the location on the model that you want to be the top and the face depth. As you can see, we can pick through the stock body to the part face. In technology, we'll assign hatch as the method we want to cut, save and calculate, and simulate this toolpath. Using the host CAD, we can see the wireframe for the center of tool movement. In the next operation, we're going to profile the inside shape of this model. The geometry selection will be done from the edges of the model, using auto constant Z to chain the entire loop. The tool selection again will come from an import library, and we'll select this 3/8" solid carbide end mill. To set the levels, we'll set the upper level to the top of the part, and we'll set the lower profile depth to the bottom of the stock model. In the technology page, we're simply going to set the finishing operation and go directly to the links to set our lead ins and lead outs. We'll use a 250 radius arc with a 45-degree angle and a G41 application distance of 10 thousandths. We'll use the same settings for the lead out. Save and calculate and simulate, and again you can see how quickly SolidCAM generates this toolpath. SolidCAM also provides templates so we can take advantage of the parameters that we've already set up. We can save the template to any name that we choose. Profile _ CAM. Now we'll come back to that template in just a moment. Another feature that SolidCAM provides is that we can do a save and copy from an existing toolpath operation to create a new one. The only thing different in this operation that I want to work with is a new geometry definition, and I want to choose that from the machined component so that we don't have the stock body in the way. So I'll choose this line as the first profile. I'll choose these 3 elements as the next profile, and I'll choose these 3 elements as the third profile. We need to change our levels by simply changing the profile depth to be on top of the pads. In the Technologies page, we're going to add in start and end extensions of 100 thousandths. We'll apply that to all 3 chains and continue. Save and calculate, and when we simulate this, you'll notice that the toolpath is on top of the tabs and is extended out from the start and stop locations as we chose. Now this is maybe a little bit of a heavy toolpath, so we may want to add another pass. By using our clear offset, we can assign an offset of 125 thousandths and then assign the same for the step over. This will give us 2 tool paths at each of the pads, reducing the strain on the tool. Now I'll exit this, and we're going to start one more tool path for profile. We're simply going to load the template that we made earlier. Now all we have to do is define our geometry, the outer profile around the outside of the part. The tool is already chosen, so we're going to reset our levels. Our profile depth is going to be at this vertice at the bottom of the part, and we'll use our delta depth to add a minus 0.1 offset also. We'll save and calculate and simulate, and again you can quickly see the system generates a tool path using the template information that we stored. One of the main benefits in SolidCAM is the ability to maintain associativity with the design model. We're going to make a change in this model. We're going to reduce the size of this tab to 0.375 on half of its width, so it's a total of 750 wide. We'll save that, save the model, and close it. When we reload the CAM project that we're working on, you'll notice that the system immediately recognizes the model change. We'll incorporate that change into our CAM project. Notice in our CAM tree, the stock and the target have been affected by this update, as well as the 3 tool paths here, but not the 4th one. From the CAM part definition, right-click, Synchronize will bring the model, stock, and target into synchronization. Notice at this point, each of these 3 tool paths need to be recalculated. Right-click on the Operations node, Synchronize and Calculate All, and that's how quickly the system generates the new tool path. And as you can see, the tool path is now updated for the model change. Hole processing can be quickly and easily accomplished using machining processes. We'll take a spot drill, and tap hole process. In this case, they're 1032 UNF holes. Notice there's only a few parameters to assign, one being the definition of the geometry. We'll simply select the top plate and pick up all the holes. Now you'll notice that the sorting order is not what I'd like to have, so I'm simply going to drag and drop this first hole to reorganize that. The depth for the top of the drill operation, be the top part of this part. The depth of the drill operation will be the bottom of the holes for the drill point. And that's all we need to set up, and you'll see the system generates all 3 operations very quickly. Utilizing standard SolidWorks assembly techniques, you can assemble your vices, your machine tables, clamps, and so forth, so that the simulation can be very realistic. When we simulate this operation, the Solid Verify simulator will show us all of these feature components during simulation. We'll slow the speed down just a little bit and play this simulation. Notice the face milling, the profiling, cleaning up of the tab tops, and then the outer profile. And in this case, we notice that the outer profile has inadvertently crashed into the fixture. Notice it shows us what operation this occurs in, and we can choose whether or not to continue monitoring. I'm going to say don't monitor it anymore, but also notice that the system now shows us the red indicating that this has gouged our vise. We've finished the drilling and tapping operations, and now we need to go back and fix what went wrong. So in the outer profile, the mistake that was made was in the levels. In the profile depth, instead of picking the bottom of the part, if we have our fixtures in place, we can actually pick the top face of the fixture and then tell the delta offset to actually stay a positive value of 10 thousandths above that. This will allow us to simulate this and show that the tool cuts the part correctly but does not violate the vise. The next thing we would want to do, of course, is produce the code. When we generate, you can see SolidCAM very quickly produces very clean G-code for any machine that you need to post-process to. Thank you for joining us in this presentation, and please feel free to visit us at www.solidcam.com.